All right, so last time we talked about how there's this drift of voltage or current, depending on how you want to look at it. But basically, the molecular structure of certain materials allow them to be more or less conductive. And so there's, well, what changes that? Well, there is a natural resistance based on the materials and the structure that occurs. And so remember, energy can't be created nor destroyed, so we're trying to count everything. So if we're got a certain amount of voltage going through a system, we should have the same amount coming out on the other end, but resistance occurs, right? Conductivity is a real thing, and we measure those things. So up here on the screen, I'm going to start to talk about the concept of resistivity, okay? And so a cylinder's electrical resistance, capital R, is directly proportional to its length, right? Because you have to push through the length of the actual object. So this is similar to like a pipe and fluid flow, right? So like a fire hydrant hose is bigger than a garden hose, so it'll carry more water. A similar thing with wires, right? So the bigger the gauge of the wire, which is actually a lower number, but the thicker the diameter, the more current it could carry with less resistance. So the longer the cylinder, the more collision charges will make with the atoms. So there's that back and forth stuff that we talked about yesterday, where the electron bounces into an atom and sometimes it bounces backwards, so it isn't always moving forward. So the longer the cable or wire, the more of that bouncing back. And so just to kind of reiterate what I was talking about, what we're talking about is that you can have like a charge, right? We'll call this Q. We'll make that a little bit bigger. So I can have a charge. Actually, that might be too big, actually. Yeah, it's a little too big. Let me change the... And so I have this charge Q, right, that starts in over here, and it'll bounce into another charge. And sometimes if it bounces into the same charge as this charge Q, it'll bounce backwards. And so it kind of does this zigzag pattern. It doesn't go straight through. In other words, it doesn't go straight through. What it does is it goes bing, 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 kind of more random. And eventually it moves through. Okay? Does that make sense? And then that capital R is the measurement of resistance, like what is holding it back, okay? So, good luck illustrating that in your notes. So that's what's going on. So obviously there's a mathematical relationship based on the volume of the cylinder. And so basically in a uniform cylinder, the length L and the cross-sectional area A, the resistance to the flow of current is similar to the resistance of a pipe and a fluid flow. The longer the cylinder, the greater the resistance, and the larger the cross-sectional area, the smaller the resistance. In other words, if we provide more paths for something to go through, we can do that. So what I really want to focus on is this right here on the bottom. We're saying that resistance, capital R, oops, wrong pen. It's written down right here. Is a mathematical relationship where rho, this is the Greek letter rho, right? The Greek is a thing that we measure called resistivity, okay? L is just the length of the cylinder, and A is just the cross-sectional area. So that's one way that we can actually calculate resistance. So this is resistance. That's an N. This is the resistivity. That's what we're going to talk about today. This is the length of the cylinder. It's cursive for length. I just realized that you guys probably don't know how to read that. And then this is area. Okay? And so this is actually the Greek letter rho. It looks like a P, but it's actually rho. So what does that mean? Well, I'm going to show you some. Resistivity is just the materials. It's a quantitative measure of a material's resistivity. So in other words, how do I find that? Well, this is a little challenging. If I take this formula and I solve, what I actually get is that the resistance times the area divided by the length will give me the resistivity. Okay? So that's a quantifiable thing that we can measure. So what I want to do for certain conductors, I have this table. I'm going to just copy and paste it. Let's hope that it copies pretty good. Oh, it won't. I'm just going to show it on the screen. So in your textbook, we have these measurements. Whoops. So these are common resistivities of different materials. So silver has this resistivity. Okay, and this is the units. It's ohm per meter. Okay. And copper and gold and aluminum. So different conductors have different resistivities. And we know this because scientists have measured these things. And these are averages. Okay. And so for your homework, if you need to find that, that will actually be in the book. The reason it's meters, remember that resistance is, and this unit is ohms per meter, because this is meters and this is meters squared, right? Those will cancel. This is meters, right? So this is like ohms, this is meters squared, and then this is meters. So one of these meters down here will cancel one of these meters, and this is our unit for resistivity. Okay. All right, moving along. Well, how does that work in the real world? Okay, so let's do an example problem of that. Calculating resistor diameter. Okay. A car headlight filament is made of tungsten, and it has a cold resistance of 0.35 ohms. If the filament, so let's write that down, resistance is equal to 0.35 ohms. I need better software. Okay. And then the cylinder, it has a length of 4 centimeters, but remember, we've got to convert that to meters. So 4 centimeters is 0.04 meters. What's the diameter? Okay. So to find the diameter is part of the cross-sectional area. And remember, the area of a circle is equal to pi times r squared. And the only thing we don't have is the resistivity of tungsten. So I'm going to have to look that up in the textbook. Okay. Now, I'm just going to do that on the other screen. But what's my relationship? Well, if I take that formula that we have up above here, this formula right here, this bad boy right here, and I do a little algebraic manipulation. In other words, I'm going to start with R is equal to rho L over A. And then if I multiply both sides by A and then divide them both by R, this cancels here. These cancels here, and I get that the cross-sectional area is equal to the resistivity times the length by the resistance, capital R. And the only thing I have to do is I have to look up this resistivity of tungsten. So if you look that up in your book, it is 5.6 times 10 to the negative 8, and that's ohms per, or ohm meters. Okay, so then to solve this, I just plug in those numbers. I know what my resistivity is. It's 5.6 times 10 to the negative 8 times the length, which is 0.04 meters, divided by the resistance, which is 0.350 ohms. Now if I plug that in the calculator, I should get 6.4 times 10 to the negative 9 meters squared. So that's my area. Okay, well that's cool. We know what the area is, but the diameter, I've got to pull that out. So one way you could do that is if I go up here, remember that the radius is equal to the distance divided by 2. So if I take this line, I could say pi times, in parentheses, the distance divided by 2 squared. Well, algebraically, that's the same as pi times d squared over 2 squared, which is 4. So now the only thing I have to do is on this side of my equation, I know that the area is equal to pi times the diameter squared, we'll use a capital D because that's what your textbook does, divided by 4. Okay, so to find the diameter, I'm going to multiply both sides by 4. That cancels, right? And then I have 4 times the area is equal to pi d, diameter squared. So I divide both sides by pi. These pi's cancel. And then that gives me 4a over pi equals d squared, but I would want the diameter, so I take the square root of both sides. And so that gives me the diameter is equal to the square root of 4 times the area all over pi. So then to finish this problem, I'm going to take this number here, the 6.4 times 10 to the negative 9, and plug that in for my area. So to find the diameter, I'm going to say the square root of 4 times, we'll just do parentheses, it's easier. What was that number again? 6.4 times 10 to the negative 9. So 6.4 times 10 to the negative 9 all over pi. That's it. And so if I crank through that and do that in the calculator, I get 9.0 times, and I'm approximating, and we're rounding some stuff. So that's a very small diameter. It's a very small diameter. Okay, so this is a very thin filament, right? So it's 10 to the negative 15, so it's a very tiny filament. Okay, and that's basically how you could use that. Now, the next thing I want to talk to you about is temperature and the variation of resistance. So temperature plays a huge role, and basically the resistivity of something can change. So there's this relationship between the initial resistivity and the change in temperature. Oh, that's not the right letter. Temp. Okay. And so this is alpha, the Greek letter alpha, and so we would call this the temperature coefficient for resistivity. So again, these are numbers that you could plug in. You have to look them up from a table. It'll be in the textbook, but you could Google them. This obviously is the change in temperature. And this is going to be the initial resistivity. And then this, of course, would be the final based on the temperature. And so the reason this takes place, we've talked about this when you think about phases. The more temperature, remember that if you have an increase in temperature, you have an increase in kinetic energy, and that affects the molecules. They're further away from each other. If the temperature goes down, though, same thing. If the temp goes down, then that kinetic energy gets transferred into some other form of energy. Okay, so there's a little bit of a relationship between that, and that has an impact on the molecular structure. So if we're really trying to figure out what's going on, in other words, when you start pumping electricity through a conductor, it'll heat up because of the resistance, and then once it heats up, that has an impact on the resistance. It could be more resistant. Okay, and so it's not dynamic where it's just one thing and then another thing and then another thing. So I'm going to pull a chart up here, and we'll look at what that means. So here is a chart. Okay, and in this chart, what we're looking at is the resistance of, what happened to my chart? Okay, what we're looking at is the resistance of a sample of mercury. Okay, now this is the temperature in Kelvin, right? And it's almost 0 degrees, but at 4.2 degrees Kelvin, there's a significant jump in resistance. And so what you see is it's a superconductor up to, okay, in other words, there is 0 resistance all the way up to the temperature of 4.2. But then after 4.2 Kelvin, now it has resistance, right? It has some resistance. So we consider this to be a superconductor as long as it's cold, right? Above that critical temperature, its resistance makes a sudden jump and continues to climb. So as the temperature increases, right? So as we go further this way, that's an increase in temperature. You see the conductivity or resistance increase. Okay. Again, our alphas are going to be in our textbooks, so let me just show you that. Our coefficients. So this would be our coefficient alpha for silver and for copper and gold and aluminum. How do we know these things? Scientists have done the work, right? And this is, if we were to explain it scientifically, it's just based on the molecular structures of these elements or materials. Okay. All right. So those you could look up for your homework problems. They're right there in the book. And so let's do an example problem. Oh, wait. So one last thing that I want to do, and then we'll do the example problem. Remember that we said that the resistance is equal to rho L over A. Okay. So now if I take rho initial times 1 plus alpha times delta t, and I take this equation here and I solve for rho, we get that rho is equal to R A over L. So then I could take that and plug that in for this over here. Okay. I could say that this is the final resistance times the area, but the area doesn't change, over the length is equal to the initial resistance times the area times the length. And then all of this gets multiplied by 1 plus alpha delta t. Oh, I hate when that does that. There we go. All right, so now what? Well, algebraically speaking, we can cancel this. If we divide both sides by A, right, those will cancel. If we divide both sides by L, those will cancel. So we actually have a formula where we have the resistance is equal to the initial resistance times 1 plus alpha delta t. Because this is what we use it for, really, is trying to figure out the resistance. Because resistivity is something we can plug in, but we don't need to. We do talk about different materials, and it is helpful, but really what we want to do when we're creating circuits is we want to know what happens to the resistance, okay? There's an example in your textbook of a thermometer and what happens as the temperature goes up. And so basically we want to know those things and how it has an impact. Let's do one example problem. How about that? See if that helps. So let's do this over here. Okay, good. And we're going to I don't like the way that that recorded that, so let's do this. All right, so although caution must be used when applying this formula for the temperature change greater than 100 degrees Celsius for tungsten, equations work reasonably well for very large temperature changes. Okay, what then is the resistance of a tungsten filament from the previous example if the temperature is increased to 20 degree, from 20 degrees to 2,850 degrees. All right, so let's do it. We say that the resistance is equal to the initial resistance times 1 plus alpha delta t. Well, our initial resistance, remember from our previous example, was 350 ohms. Times 1 plus alpha for tungsten was 4.5. You have to look this up in your chart. Times 10 to the -3 times the temperature difference. So I have the final temperature is 2050 minus the initial temperature, which is 20. So that's easy. We could do that in our head. 2,830 holy parentheses Batman, and we end up with 4.8 ohms. Okay, so that's a significant temperature increase. And so let's think about that. If my temperature goes up, my kinetic energy goes up. That means if I have a molecule here and a molecule here, they kind of move further away. They oscillate, but they're further away, so it's a little more challenging for them to conduct. Remember, the electron kind of moves another electron out of the way, so it has to come into contact with another electron and stuff like that. So basically, the resistance increases. Okay, that's it. A lot, significantly. So we started off with 0.35 ohms, and then we ended up with 4.8 ohms. I am going to do one more thing. There's not really a lab on this, although I'm going to give you a lab. I just want to show you a real-time illustration of what takes place when you manipulate the temperature with regards to the resistance. Okay, because they're all connected for sure. So give me 1 second here. Let me load this up. All right, so we have just this wire, right? And if I increase the resistivity, which is based on, and this is all based on these mathematical relationships, right? My resistance increases, right? So if I have something like copper, I have a low resistivity, then my resistance overall in ohms is less. But if I have a lot of resistivity, that's okay. If I increase the cross-sectional area, right, and this is a cross-sectional area of 15 centimeters squared, okay? Notice that my resistance goes down. If I wanted to manipulate my resistance and have it go down more, I just lower my length, okay? So we can actually make resistors. Resistors are something that's important. How do they make a resistor? Well, they manipulate the length and the cross-sectional area of known materials that conduct electricity but have a certain level of resistivity. That's why they're kind of like little cylinders. If you've ever seen a resistor, let me pull one up so you can see it. And there's other ways that they do this, but let me see if I can pull it up in here. So elements, resistor. There's one. So this is an element. You have the current that goes through here, and then it meets with some resistance inside of this cylinder, and then that resistance has an impact on the voltage or current as it comes out the other end. And so this resistors help us manipulate basically voltage and current, right? Because of that VIR, right? So remember that voltage, how these are all connected. Remember that voltage is equal to the current I times the resistance. Does that make sense? So if I increase the resistance, I might increase the voltage, but we really don't, you can't really, I mean, you can decrease the voltage. It's kind of hard actually, but usually we manipulate the current, right? So if I increase the resistance, then my current has to go down, or then vice versa. And we do this through math. But basically, that's how we control things. We have resistors, we have transformers, and all of them manipulate the flow of electricity essentially the way that we want.